So, welcome back. We have been looking at description logics and we have seen how to form new concepts from a set of primitive concepts, new relations from a set of primitive relations, and how to express sentences in description logics. It basically are about subsumption and membership. So, let us look at the process for reasoning in description logics, and the algorithm that we use is the Tableau method, which you might recall we had studied when we were looking at propositional logic. The idea is similar. It is like model checking, that you give some input to the algorithm and it tries to find a model for you. If it cannot find a model for you, that means that the original input is unsatisfiable. So, something similar we will do for the kind of conclusions that we can draw in description logics. In particular, we will focus on this simple description logic ALC, but you can imagine that the method can be generalized. So, this is the language ALC that we spoke about. Just to do a very quick recap, concepts can be atomic concepts, top, bottom, or some A, or they can be constructed using any of these other concept forming operators, which includes negation, intersection, union, and role restriction. And the kind of statements that we are interested in is that a concept C is subsumed by a concept D, or it is equivalent to a concept D, and that an individual A belongs to a concept C, or a pair of individuals belong to a relation or role R. So, whatever we discuss in description logics is often implemented using the web ontology language OWL, and this is how a sentence in OWL would look like. So, this is just to introduce to you the fact that you can use a tool called Protege to express or construct ontologies in OWL. And OWL, there are different variations of OWL, but there is a variation called OWL DL, and that OWL DL corresponds to whatever you can say in description logics. So, here is just a snapshot of how you would express things. So, you can see that there is a concept called Apple device, there is a concept called happy, and it has a subclass called TOAD, and there is a concept called person, there is a concept called teen, and teen also has a subclass TOAD. TOAD stands for teens who own Apple devices. And what we are saying here is that if someone is a teen and owns an Apple device, then they are a subclass of the class of happy individuals. Here are some examples in OWL. So, you can see here that we are talking about the equivalence relation here, and this is expressed by the fact that we are talking about equivalent classes. There are two classes. One is just a named class called toad, the other is an intersection of two classes. So, this is intersection here, as you know. One of them is teen and the other is this concept which says that you have some values for the role owns from Apple device. So, teens, you have to be a teen and you have to be someone who owns at least one Apple device, and we are saying that the name toad applies to this concept essentially, and then we can say that toad is a subclass of happy device. So, whenever you are looking at DL statements, you can also think of them as an implication statement. So, it basically, as we saw this earlier, whatever we can say in description logic, we can say in first order logic. So, essentially what this is saying is that if someone belongs to the class Toad, then someone belongs to the class Happy. So, then you would think of this as an implication sign. Here is a grandchild relation. So, we are saying that there is a property chain which is has child followed by has child, and that this property chain is a sub object property of something called has grandchild essentially. So, if you have a child who has a child, then you have a grandchild. You are saying that the domain of the child property is a person essentially. So, the property is has child and the domain of that is person essentially. The range of has child is also a person essentially, and you can express them in description logics as shown here, that if you have a child, if you have at least one child, then you are a person, and that everyone is belongs to the class that if they have children, then the child is a person. We also spoke about the inverse earlier, and that basically here it says inverse object property. So, this is OWL language, and whatever we could say in description logics, we can say in OWL essentially. Now, the process of reasoning for description logic involves converting everything into a form known as the negation normal form. This is very similar to the clause form or the conjunctive normal form that we use for resolution refutation method. It will also have the added similarity that if you want to show that something is true, then you might want to add the negation of that to the set of to the knowledge base essentially. But first let us focus on how to convert things into negative normal form. So, if you have an equivalent statement, you reduce it to two subsumption statements, and if you have a subsumption statement, then you reduce it to a concept essentially. So, you have to think a little bit carefully here as to what is happening, because what you have on the left hand side, C subsumes D is a sentence, it is either true or false essentially. Whereas, what you have on the right hand side, what you are converting it is to a concept essentially. So, if you remember what C subsumed by D says, that for all x, C x implies D x. If you look at the semantics of this, then what you are saying is that you have a concept C and it is contained in the concept D. So, this is C and this is D, and of course, there is a universe of discourse or the thing concept or the top concept essentially. Now, what have we done here? We have said complement of C union D, and if you think kind of correlate this with logic, you will kind of associate it with not C x or D x, which as you know is a way of writing the implication. You can write it as a distinction as well. But how does this work for reasoning? Now, remember that the Tableau method is basically a model checking method. It is looking for a interpretation which is a model essentially. And what is this particular set saying? That you are it is a union of everything that is not in C and everything that is in D essentially. So, if you think about this carefully, you will see that this is the entire domain, because everything that is not in C is outside of C. So, it must be from the domain, and the rest is from domain D. So, in some sense this corresponds to the full domain essentially. So, you can think of it as corresponding to something which is true. What if C was not subsumed by D? If C was not subsumed by D, then it could possibly be something like this. So, this is C and this is D. Now, what does our concept denote? It says that it is the union of not C with D. So, let us first look at what is not C. So, not C is everything that is outside C. So, what I have shaded now is not C essentially, but this is the union of not C and D. So, we have to include everything that was in D as part of this. So, now you see that it is not a complete universe of discourse. There are some things which are not in this thing, and that happens when C is not subsumed by D. When we saw that when C is not when C is subsumed by D, as we saw, everything would be included in the set. Now, the Tableau method, like the one that we studied earlier, would take the negation of what you want to prove and add it to the set of sentences, and then try to find a model for that. So, by negation in the concept world, we mean complement. So, what is the complement of not C union D? The complement of not C union D, the complement is the empty set, as you can see here, provided that C is subsumed by D. But if C is not subsumed by D, then we have seen that the complement of not C is not C union D is not empty, as we have drawn on the right hand side. So, here let me write this, that C is not subsumed by D. So, there is something which is remaining essentially. Now, if I take the complement of that, then I will get this moon like shape, which let me shade with the vertical line. So, that would be the complement of not C union D. Now, that is a non-empty set. So, that means it is satisfiable, and which means that we do not have a model for the negation of not C union D. Whereas, if C is indeed contained in D, then the complement would be the empty set. If it is not contained, then the complement is not the empty set, and this should hopefully give you some intuition as to how does the Tableau method work essentially. So, we take a sentence which has truth values, we transform it to the domain, and now we are looking for a model essentially, or satisfiability essentially. So, let us look at this a little bit in more detail. First, how to convert things into negative normal form. We have already said that we will transform this into two these things, the equivalence into two subsumption relations. If we have the negative form of C subsumed by D is the negative normal form of not C union D. So, we have made this transition from a sentence to the domain essentially. In some sense, that is a semantic approach. So, model checking is like a semantic method. We are looking for a model which will satisfy the sentence or which will make the sentence true. Then there are some other things that if you have negation of top, then it is bottom, and likewise negation of bottom is top. the NNF of A is A itself, the NNF of not A is not A, the NNF of not C is C, and if you look at the binary operators, then you basically push the negation NNF form inside there essentially. And like in the De Morgan's laws, we flip the nature of the operator essentially. So, once you push the not inside here, then this intersection changes to union. So, we are used to this by now. Something similar happens for role restriction also, that once we have negation here and once we push it inside, the nature of the quantifier changes. So, for all becomes there exist and there exist becomes for all. So, that tells us how to convert everything into NNF form, and now we are ready to talk about the algorithm. This is an example of converting things into negative normal form. So, you see that first we have eliminated this and replaced it by this and by this, and then we have pushed the not inside here, and then we have replaced this by A, and then we have pushed this not inside here, and that has become for all now, and now we have a compound concept essentially. So, we are talking about entailment and we are talking about interpretations because we are looking for models. So, just to do a quick recap, that interpretation is a mapping that denotes for something in the domain. Concepts are sets of objects, and you can see that things like teen, apple. So, when you say teen superscript I, basically we mean the interpretation of teen. So, the teen is a expression in the description logic, it is a concept in the description logic, but teen superscript I is a set in the domain essentially, and that set is a subset of the domain essentially. Likewise, roles are subsets of domain cross domain, and objects are images or interpretations of those individuals. We say that an interpretation I is a model of alpha if the interpretation satisfies alpha. That means that alpha can be made to be true, that such a concept does exist. It is a model of a KB if it satisfies all the sentences in that KB essentially. And a model is an arrangement or a configuration of the world that makes that alpha true essentially with respect to the knowledge base. So, if you have a set of sentences which form the knowledge base, there will be a combination of T box and A box sentences. Remember that T box is a terminology box which does not talk about individuals, but of relations between concepts and roles and so on, whereas A box talks about individuals essentially, the assertion box. So, alpha is satisfiable if it has a model, the KB is satisfiable if it has a model, and a KB entails alpha if every model of the KB is also a model of alpha, and this will be true if we add the negation of alpha to this, and then the whole thing becomes unsatisfiable. So, to show that KB entails alpha, you add the negation of alpha to the KB and show that it becomes unsatisfiable. So, you would recall the resolution refutation method, we did exactly that essentially, and also in the Tableau method that we studied for propositional logic. Now, in general there would be many models, because we have been saying repeatedly that we are talking about the open world domain. So, it is not that everything that we know has been expressed in our set of sentences. There may be other things that we do not know, and many of those other possibilities would be included in models. So, in that sense we can have an infinite number of models in this thing, and that is the open world assumption that we are talking about here. And we are going to be working with that essentially. So, what are the kind of inferences or the questions that we can answer? What are the inference problem that we can address in description logic using the Tableau method that we are talking about? So, the first thing is class equivalence or C and D equivalent, then class subsumption, this is the most important. Is C a subclass of D? Class disjointness, are C and D disjoint? By this we mean that there is no overlap between the two sets. Is C satisfiable, which means can we find an individual which belongs to the class C? Is the knowledge base satisfiable? Is every concept in the knowledge base satisfiable? Is C of A entailed, which means that given an individual A, it belongs to the class C. Can we show that? And then we can say list all members of C. These are the questions that we would like to address, and we will take this up in the next session.